I talked about efficient flow pollution. The intuition is fairly simple. It's an equimarginal principle. The marginal benefits of the polluting activity should equal the marginal damages of the pollution. And the important thing to keep in mind there is that the polluting activity is typically beneficial if we disregard the pollution. The intuition was fairly simple. The math was pretty straightforward as well. I'm now going to look at efficient stock pollution. The intuition there is also simple, that marginal cost should equal marginal benefits, but because it's now a dynamic problem, the mathematics are a bit more complicated. So we're going to assume that the polluting activity just generates a flow of pollutants m, and it just depends on what happens at any time t, and there's no dynamic there whatsoever. The damages of pollution now depend not on emissions m, but rather on the stock of pollution a. So that is the main difference here. It was d as a function of m, it's now d as a function of a. And the stock of pollution, let's assume that is a first order difference equation, that is the stock of pollution A at time t depends on the stock of pollution A at time t minus 1, and part of it is assimilated in the environment. Part of it disappears through natural processes. But of course we add to it by emissions m at time t minus 1. And this is an equation that is structurally the same as the accumulation of physical capital, where you can think of m as investment and delta as depreciation. The interpretation is different, but the mathematical form is of course the same. At any time, the net current benefits, the benefits of emissions minus the damages of the stock of past emissions. And we want to find the efficient amount of stock pollution, so we want to maximize not the net benefits, but rather the net present value of those benefits. And that is given here, net present value of the benefits. And there's two ends here. But really, we're talking about net only once. The net present value of the benefits equals the present value of the net current benefits, that is the benefits of the polluting activity at time t minus the damages of the stock of pollution at time t, and of course we want to discount that with a discount factor, a discount rate rho. The first order conditions for optimality, and there's now multiple conditions, there's now as many first order conditions as we have time periods t, is still that the marginal benefits should equal the marginal cost. So the marginal benefits is the b dm t, and that is evaluated at time t, so that needs to be discounted with a discount factor 1 over 1 plus rho to the power t, right? The marginal benefits are the d, the m at time t, 1 over 1 plus rho to the power t, but the d, the m doesn't exist because d depends on a, but a depends on m, so this is the chain rule, the d, the a, the m, right? So this is how damages respond for a change in the stock of pollution, and this is how the stock of pollution changes in response to the change in emissions, right? So that is one thing that happens. The key thing here is that this doesn't just happen at time t, but if we have emitted stuff at time t, then there's also still more pollution at time t plus 1 and at time t plus 2 and so on and so forth. So if we set S as 0, then we have the d, the at, the at, the mt, with a discount factor 1 over 1 plus rho to the power t, same as here. But then that year after, s is 1, there's also stuff added to the stock, and that also does damage, additional damage, and so on and so forth. And that is a flow of additional pollution from now into the indefinite future, right? So the big change here is that we have the B, the M, and now we have the D, the A, the A, the M, but we have a flow of these things into the future, right? So that is the main difference between stock and flow pollution. It's still marginal cost should equal marginal benefits, but the marginal costs are now a stream of costs from now until the future. Now, this is a pretty awkward expression, but we can do more of it, more with it. So because we assume this first order difference equation, really what we have is that we put stuff into the atmosphere now, a year later 1 minus d is left, a year after that 1 minus d squared is left, a year after that, and so on and so forth. So that becomes 1 over 1 plus delta to the power s, right? That this expression here is replaced by this expression here by assumption, right? Now, this thing here, 1 over 1 plus delta to the power s times 1 over 1 plus rho to the power s is approximately equal to 1 over 1 plus delta plus rho to the power s, right? So the equation looks slightly friendlier, not a whole lot. Now let's assume that things are in a steady state. That's always a handy assumption to make. And what does a steady state mean? It essentially means that you can get rid of your substrates. So steady state means that the level of environmental pollution, the stock of environmental pollution at time t is always equal to A. So you can essentially drop the subscript. That means that the accumulation function becomes A is 1 minus delta times A plus M, or A is M over delta. So that is a handy expression. We got rid of the t's, so the first order condition is the B, the M is the A, the M. No longer depends on t, so we can bring it in front of the summation sign. We have this expression here, 1 over 1 plus delta plus rho to the power s, from now until infinity. So we actually know what this expression here is 1 over 1 minus 1 over 1 plus delta plus rho. You can work that out, that is this expression here. And now this thing kicks in because we still have the d, the a in here. We still have a d, the a in here times this awkward term. But we know the relationship between a and m, and that means that the d, the a is equal to the d, the m times the delta. So now we're there, we have essentially the same expression as we had for efficient flow pollution. The B, the M, the marginal benefits of the polluting activity should equal the marginal damages of pollution, just as we had before. And then we need to put in a correction factor that essentially says this is not a flow pollutant, but it's a stock pollutant. It accumulates in the environment, in the atmosphere, in the water, or in the soil. The principles are exactly the same. It's an equimarginal rule, right? Marginal cost equal marginal benefits, but marginal costs are now the present value of a flow of costs into the future. And essentially, because we put everything into steady state, you can see this as a perpetual annuity. So that is one interpretation. The other thing that is happening here is that this decay rate delta is essentially just added to the discount rate row. Now what is discounting? And discounting essentially means that money in the future is worth less than money today. Money gradually disappears from the, as you look further into the future, you care less and less. £100 today is worth more than £100 a year from now. That is discounting. And essentially, you care less about future money than you care about today's money. That is discounting. And the delta is just added to the discount rate. And it has very much a similar interpretation, because this equation here tells you, well, if you put pollution into, say, the atmosphere today, there's a lot of pollution today, but only a fraction of that remains next year, and a smaller fraction remains the year after that, and a smaller fraction remains the year after that. So you actually care less and less and less about the pollution that you put into the atmosphere in this case. So essentially the problem melts away, just like discounting lets future money melt away. In this case, the physical problem or the chemical problem or the biological problem gradually disappears. It melts away, so you care less. And that implies that the environmental decay rate, delta, essentially works the same way as a discount rate.